The problem goes like this. Supposing this is a environment in which the temperature is theta naught. And there is a body which was being maintained at a temperature of theta, which let us assume is higher than theta naught. And that body is suddenly brought and placed in this environment. Its temperature at any instant of time is theta. It started with theta I, let's say 100 degrees Celsius or 180 degrees Celsius, and let us say theta naught has a certain value, maybe 25 or 20 degrees Celsius, maybe 40, whatever. We will see those points later. So the problem is that a body which was being maintained at a temperature of theta, we'll call this theta initial I. In an oven, let's say, it is a hot body, it is suddenly brought into an environment which has a temperature fixed at theta naught. So how will the instantaneous temperature of this body vary with respect to time, and we can say how long will it take for this body to come and cool down to this particular temperature. It's evident that ultimately the temperature will fall till it reaches the temperature of the environment. It cannot fall below that. So let us write the law of cooling, which was enunciated by Newton, and try to solve the differential equation. Newton stated that the instantaneous rate of cooling is proportional to neither theta, not to theta naught, but to the difference between theta and theta naught at any instant of time. The instantaneous rate of cooling, let's say of a hotter body, is proportional to the temperature difference at that instant between the hot body and the ambient temperature, which remains constant. So we will write this in terms of mathematical symbols, and this is nothing but d theta dt is proportional to theta minus theta naught. That is it. That is the problem formulated as per the physical law stated by Newton. That is, the rate of cooling, instantaneous rate of cooling, is proportional to the difference in temperature. This is the difference in temperature between the hot and cold body. That's fine. Now, if we just care to remove what we have written on top and just dwell on this particular equation, we will see that we can remove the sign of proportionality and replace it by a constant. And again, we will discuss on the sign, SIGN, of that constant. This can be written as d theta dt is k into theta minus theta naught. Now, it is a matter of, I think it's a very simple matter to appreciate that because theta is higher than theta 0, and we are talking about cooling, the rate must be negative, and hence this particular k has to be negative. So as we have done before, we will write minus k. And if we say that k is positive, then that ensures that minus k is negative. So we have indeed cooling and not a rise in temperature. Although, of course, in an extended way, the Newton law of cooling can be extended to see how the temperature of colder bodies rise as they are brought into a warmer environment, just the reverse problem. So here what we do is, we write this as d theta divided by theta minus theta naught is minus k dt. If we just integrate this, the next step, we can write this implies log base E theta minus theta naught is minus kt plus a constant. Again, we are left with the task of determining the value of this constant C. And that's simple because, as we stated in the beginning, let us assume that when T is 0, that means from the point of time when the body is brought out from the oven or wherever it was and placed into this cold environment, if that point of time is considered as T is equal to 0, then we agreed that the temperature of that body was theta I, theta initial. So this implies that log E theta I minus theta naught is plus C because T is 0. T is 0, so this is the value of C. We can put it there. C is log of theta I minus theta naught. Go a little bit on top. C is so our equation becomes log E theta minus theta 0 is minus kt plus this constant. So becomes log E is minus kt plus that's it. So we can now in fact transport that term on this side and write the following. Log base E, if there is a theta minus theta 0 here and theta I minus theta 0 here, we can put this as log E theta minus theta naught over theta I minus theta naught is minus k t. Removing this logarithm sign, this implies that theta minus theta naught is equal to theta I minus theta naught times e to the power of minus kt. Now, this particular fellow is a constant because the initial temperature will have a certain value and theta naught is the ambient temperature that has a certain value. So what we can do is we can write this as equal to, say, let's say theta difference, initial difference in temperature between the hot body and the cold body times e to the power of minus k t. So that is the final equation. In other words, we can write theta as theta 0 plus the initial difference into e to the power of minus kt, which we'll do up. We write the final result in a simple way. Now the question is, should we believe this result? That's very important, whether we should believe this result at all or not. The answer is in the fact that if we take a limit of this as t tends to infinity, one must appreciate that this theta is actually nothing but theta as a function of time. So, once we take a limit of this as t tends to infinity, which is a very large number of time units, the value of this temperature of the hot body will settle down to this. That is what we should expect, and that is what the equation says, because as t tends to infinity, e to the power of minus kt tends to 0. So that is absolutely justified. As limit tends to infinity, e to the power of minus kt tends to 0, and of course theta tends to theta naught, and one can write as expected. Nothing else is expected. So when such things happen, that means the mathematical model and solution leads us to natural expectations, then we know that we are on the right track. Otherwise, we are not on the right track.